Okay, good evening. I hope we are a bit, no, I can see we are a little bit behind on the schedule. We will conclude with the last presentation. It's regarding enhancing ping and TRACEROUTE, which is popular IP OAM tools. We will be having this presentation delivered by Mr. Ron Bonica, distinguished engineer from Juniper Networks, and together with Mr. Andreas Roeseler from Harvey-Mudd College. As a note, Ron is presenting for a second time in vGRNOG. Hopefully, circumstances allow, we would like to have him as a presenter in an in-person meeting of ours in Greece. And as far as I know, he speaks a little bit and understands a little bit of Greek, so it would be a nice opportunity for him to improve his Greek language skills. So, Andreas and Ron, the floor is yours.
Well, thank you very much. Thank you. Ping and TRACEROUTE are the two most common OAM tools in the internet. You probably use them 100 times every day, don't even think about them anymore. Well, we thought about Ping and TRACEROUTE a few years ago, what they can do, what they can't do, and decided to enhance them a little bit. A couple of years ago, I wrote a couple of internet drafts that have become RFCs. And this year they were implemented by some students at Harvey-Mudd College. If we could go to the next slide, Andreas. Here's the team, the developers from Harvey-Mudd. You'll hear from Andreas in a little while. Zach Dodds and I were the advisors to this team. And at this point, I will hand it over to Andreas and let him talk about the work he did.
Awesome, thank you, Ron. So, like Ron just said, we're going to be talking about ping and TRACEROUTE in this presentation. And at the highest level, we're going to try to draw a distinction between nodes and interfaces, where we're defining nodes as a host or a router on the internet that communicates to other nodes via its interfaces, which actually send and receive messages. And we're going to find out that the issue that we recognize with ping and TRACEROUTE is that they only can determine information at the node level, where a lot of the times you want to figure out what's going on at the interface level. So for the rest of this presentation, we're going to follow this kind of roadmap for both ping and TRACEROUTE. We're going to look at what they do, how they work, what they can't do, which again is going to tie back to the difference between nodes and interfaces, and what we've been doing to try to enhance these tools. So let's begin looking at ping. So ping tests the liveliness of a reachable interface, and you use it typically to test the liveliness of a reachable node by testing the liveliness of one of its reachable interfaces. So you send the message to its interface, and then it will respond, and that's how you will know the node is active. And it really does this by sending an ICMP echo to the probed interface, and the probed interface will reply with an ICMP echo to the probing node. So now we're going to go to the section nerd notes, which is kind of zooming in, getting a bit more technical details instead of a very high level overview. And important things to note are the echo request can enter the probe node through any of its interfaces, and we really don't have any control over which one it enters. That's due to factors such as the network topology that we don't really have any control over. Similarly, the echo reply can leave the probe node through any of its interfaces, and we have no idea which one it may leave through. So there's really no guarantee that either message traverses the probed interface that we might like to know more information about. So to say it out explicitly, it can't test the liveliness of less than reachable interfaces, which might be a problem because an interface might be not working and therefore it's less than reachable, and we would like to know why it's not working or what its status is. Or it could be a fully functional node, but is more difficult to reach through the traditional ping command, such as an IPv4 unnumbered interface using anycast addresses, IPv6 unicast with narrowly scoped addresses, or any interface to which the probing node lacks a direct route. So all these interfaces we actually can't really learn anything about with the traditional ping command. So what we've been doing is implementing RFC 8335, which was co-authored by Ron. And what this does is adds an extension to the ICMP echo request that contains information about the interface we're trying to learn about. So instead of just a ping message that says, "Are you alive or not?" We're trying to say, okay, is this interface working? What is its status? And we can gain a lot more information that way. And what the interface will, and what the receiving node will do is it will look at that information, then query that interface and reply back to us with more information. So let's look at this as a bit of a diagram. So let's say my colleague Nick would like to figure out what is going on with interface 3 on the proxy node. But due to network conditions that we can't control, all of his ping messages are going to interface 2 on the node. So with the regular ping command, we're kind of stuck here. There's not really anything we can do to query interface 3. But if we use the probe command, we can specifically ask, how is interface 3? And even though our message is getting to interface 2 on the node can respond to us the status of interface 3. So therefore, we're learning information that would otherwise be inaccessible without the probe command. So for a bit more details, the proxy interface can be different from the probed interfaces, and often is different because, like we're saying, we don't have any control over the network, over which interface we arrive on, so we can gain information about other things through the probe command. So the proxy interface must be reachable for the probing command, similarly to ping. However, ping is limited because the proxy interface must be on the same node as the probed interface. Whereas with probe, it can be on the same node, or it can be a node that's directly connected to the node that our message is actually getting to. So we kind of extend the range of the information we can get with probe by one hop. And this can be useful for things such as NAT boxes to get past those. So let's take a look at what this might look like if you were to use this. So here is a terminal output of using the ping command with the extension. So for the ping command, we specify the -4 to just make sure it's IPv4. And then this is the work we've been doing where we added this -E flag, which means that we're extending the ping message. So using the extension structure, and the next item is the identifier for the interface we're looking for. In this case, we're identifying the interface by GE-0/0/0, and this interface is on the node specified by that IP address. So then we get a very, very typical ping output that you might be familiar with, but then in the statistics section on the far right, we actually have another bit of information that we're getting. We're getting the status, and now we're seeing that this interface on the node, specifically, not just the node itself, is active, and it is receiving IPv4 and IPv6 information or messages. So here we can get a lot more fine-grained information about interfaces on the node. So this is giving out more information that wouldn't otherwise be accessible by our network. So that brings with itself some security considerations, because obviously we don't want to give out information about our network to people who have malicious intent. So to address these problems, we have made sure that implementations do not enable this by default. So you have to explicitly turn it on in order to receive messages. You can do your debugging and then turn it off if necessary. And there are also options to make sure that this information can only be accessible from a specified source address. So if you send a message from a recognized address, it will respond with the probe information. Otherwise, it can drop the packet or just respond with a regular ping, whatever you would like to have. And there's actually a decent amount of support for this technology already. So Juniper, in its Junos 20.3 R1 line, supports this functionality as of right now. Similarly, our work this semester, we have added this functionality to the Linux kernel. So Linux routers that use Linux of the version 5.12 or newer will support this functionality. And so the Linux kernel has responses to these. In order to actually send these probe requests, you need to use the IP utils package, which is the most popular package that includes ping. And we are currently working in getting our work submitted to that package. So once both of those are in, you will be able to send and receive probe messages from Linux machines, which is very useful. In terms of dissectors, Wireshark, as of 3.4.4, which is actually a very old version, supports dissecting these messages, so you can use that to confirm the packets going in and out. And we have submitted work to TCP dump, which is currently in review. So all these currently support, or will hopefully support, this technology in the near future, which is great. So now we're going to switch tracks and talk about TRACEROUTE. And the presentation is going to have a very similar structure to what we just went through with ping. So what does TRACEROUTE do? So TRACEROUTE sends a series of successive messages to elicit feedback from each node along the delivery path between a source and a destination. And you can identify the nodes along the delivery path. And again, we can only get information on the node level, which actually might obfuscate or kind of hide information that we would want to know about. So TRACEROUTE does this by sending a series of UDP packets from a source to a destination, and it uses the time to live field, or TTL, in order to do this. So it sets the TTL to 1 on the first packet, so the message gets to the first hop along its path, expires, and then that node will send an ICMP time expired back to the source, and it increments that on each hop. So to get a bit more technical, the UDP probe messages by default have the UDP source destination port to 33434, and it's incremented in each subsequent packet. And for the ICMP time expired messages that the node sends back to us, the source address may not identify the interface on which the UDP probe message arrived, which can actually be a pretty big problem because the entire purpose of the command is to figure out where our messages are going. But in the case of IPv4, it might identify the interface through which the ICMP message left the reporting node, which isn't where our message is actually going, it's where messages are getting back to us. So what can happen is you try to figure out where your messages are going and instead get an adjacent path, which might not be helpful at all in terms of figuring out what's going on in the network. It's even worse for IPv6 because it can respond with any number of IP addresses, and it's based on the settings of the router or the node, and we don't really know which version the node is using, so it gives us even less information. So to say this concretely, we can't identify interfaces along the delivery path, which we might want to know to see exactly where our packets are going. So this was enhanced in RFC 5837, which actually doesn't change the UDP probe message at all, which is nice because then we can send the same TRACEROUTE messages we've always been sending, don't have to change any code, and it will work. Instead, what we do is we add an extension to the ICMP time expired message. And this extension will contain a bit of information that will tell us which interface the UDP probe message arrived upon, so we can see where our packets are going. And it even can tell us the interface through which the message would have been routed if it hadn't expired. So this will tell us where it came from and where it would have gone, so then in the next hop we can verify and gain exact knowledge of where our packets are going. And the things we can learn about these interfaces are the attributes, so the name, the IP address, the maximum transmission unit, and this type of information. So this is another terminal output of what it might look like to use this command. So we just call regular traceroute, nothing has changed. Let's look at the blue boxes. So these are the additional structure that we've added. So for the example, in the 5th message, we see that the interface identified by the IPv4 address 68.1.4.252 responded to us saying that this was the hop along the path. However, the arrival interface that we see actually has a different IP address. We have its name, and its IP address actually starts with a 38. So this is telling us that our messages are actually going to the IP address with the 38. However, the 68 is responding to us. So we might want to look more into the 38 address and ignore the 68 address when we're trying to debug things in the network. So we can get a lot better. We can get a lot better idea of where our messages are going if we use this extension instead of having to make assumptions about where our messages are going or what's actually talking back to us. So similarly to probe, this has a number of security considerations because, as always, giving out information can be risky. So we take the same steps in order to kind of mitigate this concern. We don't enable it by default, so any non-enabled box will just reply with a default traceroute message, the same that it would do now. And we can even make it accessible only from certain specified source addresses. So in terms of implementation, this functionality is a lot more in progress than in probe. Probe has a couple working ones as of right now, whereas for extending trace path their TRACEROUTE, we are hopefully going to see a couple implementations within the near future. So Junos is currently working, or Juniper is adding this to its Junos line. It will start with the EX series of routers and then move along its product line. We have submitted work to get this into the Linux kernel, and it is currently under review. So hopefully in the near future that will be accepted, similar to the IP utils package. We just need to add information to print it out because, like we said earlier, we're not changing the UDP packets themselves. So that patch is sent out and we are hoping to hear back shortly. And Wireshark 3.5 can currently dissect all these messages and has no issues with that. So that was a brief overview of these two technologies, and we now would like to open the floor to any questions.
Thank you, Andreas. Thank you, Ron. Is there any questions? Yeah, there is from Ron.
Yes, if I could add one point.
Yes.
The major benefit of this is the ability to deploy nodes with unnumbered interfaces. Let's say for a minute that you have a node that has a numbered loopback interface and 1,000 unnumbered real interfaces. Well, today there's no way to ping those real interfaces. With probe, RFC 8335, you can send a ping to the one and only numbered loopback interface, asking about the status of any of the unnumbered interfaces. So it really starts to allow you to use unnumbered interfaces more. The same for the enhanced traceroute. In this node that we talked about with one numbered interface and 1,000 unnumbered real interfaces, if you did a traceroute through it, all you'd know is that the packet traversed the node. With the extension, you know which interface it entered through and possibly which one it would have left through had it not timed out.
Okay.
Back to questions.
Yeah. Kostas Zorbadelos would like to pose a question as well.
If I may, yes. Ron, you mentioned, okay, you can probe the unnumbered interfaces, but do you have to know the exact naming convention of the interfaces? So depending on the vendor, the naming convention on the interfaces are different. So would you have to know, perhaps I misunderstood, but do you have to know the naming of the interface, first of all? That's my first question.
Well, there are three things that you can do to identify the probed interface. You can identify it by name. So if you know the vendor's naming convention, you know, GE000, that works. If you know the IF index, that will also work, although it's less likely that you would know the IF index. If you know maybe a IPv6 link local address, or maybe an IPv4 private address that you do not have a route to, that would also work.
MAC address, layer 2 information?
MAC address, we don't have that. We could, but we just didn't think of putting it in.
Okay.
You know, if you wanted to do it by address, the only way we could do it is by a locally scoped address, a link local, or an IPv4 private address to which you do not have a route. Maybe one that isn't advertised.
Provided that you do have such addresses on the interface.
Yeah,
nice.
Yeah.
And could you also please share, if you know at least, what is the support of the other vendors on that? Do they have any plans on supporting it? It's very nice to see it in the Linux kernel, of course. But how about the other network equipment vendors? Do you know anything about it?
I don't know of any others supporting it.
Okay.
I'd encourage you to contact them.
As customers, most probably.
Yeah,
as high paying customers. Yeah.
Yes.
Okay. Thank you.
Okay, we have two more questions from the audience. One, it would be from Gabriel Umbe. You are free to pose your question, Gabriel.
Okay. I will have, I think, two questions. My first question is, this ICMP feature support IPv6 or it is only IPv4?
Both.
Both. Okay. My second question is, you say that it is disabled by default. And on my question, if we want to enable it, we should enable it only on in the bot on the true end equipment, so source and destination, or we should enable it only also on the full path.
Okay, it's on the responding equipment. But before I answer that question, I'd like to check with Andreas. In the Linux kernel, we did do it on both IPv4 and IPv6, no?
So it is currently in for IPv4, and we're working on getting it into IPv6.
Okay, cool.
So you can send an ICMP v4 message, and that can query by name, IF index, or by IPv4 or IPv6 address. So you can query interfaces by that. But then if you want to send an ICMP v6 message, that is currently not supported, but hopefully will be soon.
Okay. Now, to the second question, how do you secure this? Let's say we're talking about probe. Probe is typically something that you might want to be accessible with, to your NOC within your network domain, but not accessible to the outside. So you would have one switch, at least on the Junos implementation, that makes it accessible to everyone. And then you would probably want an ACL to make sure that it's only accessible to those within your network domain. So you would filter the extended echo message if it were coming from outside your domain boundary. Does that help?
Yes. But if it is inside the same, network, so it's inside the same domain, we should enable it on all the router or only the true the true end equipment.
Oh, only on the network edges, you're saying?
Yeah, look, if I want to do this ICMP from router E, from router A to router, so from router 1 to router 5. And my ICMP will pass via, will be routed via router 2, 3, and 4. My question is, should we enable this feature also on router 2, 3, and 4, or we can enable it only on router 1 and router 5?
In the example you saw on TRACEROUTE, it was enabled on only 2 routers in the path.
Okay.
And I think the reason Andreas did that was just so the result would fit on the screen. You could enable it on every node, or you could enable it on selected node.
Okay.
It depends on which nodes you want the extra information from. Typically, I think you'd enable it on every node.
Okay, thank you, Gabriel.
Okay. Thank you.
And the last question, it would be from Yanis. Yanis,
hi.
Hi.
Hello. First of all, thank you, Andreas, and thank you, Ron. And Ron, thank you for your wonderful work at the ITF Physics Ops. So, yeah, unfortunately, most of my questions have already been asked and answered by Kostas and Gabriel, but okay, I'll just reiterate through some of the stuff I've noted here. First of all, I didn't catch if there was an RFC, if there's a draft about this, or not?
Both are RFCs.
Good.
The
I didn't
ping,
get the numbers, but I guess I will find
yes,
them. Okay.
The ping extension is RFC 8335.
Yeah.
And the traceroute extension is RFC 5837.
Okay. And the next question was, yeah, I mean, at first, when the presentation started, I thought this was not like a good idea, but a bit of a security nightmare. But then Andreas mentioned that this could be limited to, enable this feature or disable it. I mean, for example, in Junos. Do you do that under I don't know, under control plane protection, where you can allow specific hosts to access this feature?
Well, there are two ways to do it. One way to do it is with ACLs, with firewall filters, and that's to say, I will only accept an ICMP extended echo request on some interfaces or from some source addresses. And another way is to turn it on and off globally, to just say, I will not accept it from anyone. And so much for that.
Yeah, I think, well, in my mind, it would probably make a bit more sense. I mean, since it sounds like a control plane feature, it could make sense if you could enable it under your control plane protection for example, for your trusted network once and for all, and you don't have to implement an ACL or a global feature.
Yes, on the SRX, where we have a distinction between trusted and untrusted networks, yes, we could do that. I don't think we've implemented it on the ACX yet. That's the one platform where we haven't done it.
Okay.
I'm sorry, not the ACX, the SRX, sorry.
Okay, thank you very much.
Thank you, Yanni. And it's also Blake Willis that is willing to pose a question.
Thanks, folks. This is great. Have you played with this at all, or thought about how this would react to ICMP tunneling in an MPLS network?
Okay, ICMP tunneling. So what you're talking about is an MPLS packet expires.
Yep.
And then you create the ICMP packet, which would be exactly what it was before. Send it to the egress of the MPLS LSP and send that back.
Right.
It should just work. Now, have I ever tested it? Do I think it will work in any implementation? Well, I'm pretty sure it won't in Linux, because I don't think Linux does MPLS at all. And I haven't tried it in my own Junos implementation.
I noticed there were a couple of new, I mean, there's an older ICMP tunneling knob, but I noticed there's one recently in like 18.4 or something that does something else with ICMP tunneling. So that might be worth looking into. It'd be interesting to see what happens, because like you're coming in on an LSP, not on an interface, right? So. Yeah,
and the other interesting thing is there would be two extensions in the time expired message. The RFC 4950 extensions telling you what the MPLS label stack looked like, plus the new extension telling you what interface we arrived on. So, gee, I should go test that.
Be interested to see, thanks.
Yeah.
Thank you, Blake. And Gabri, do you want to add something? Nope, most probably. It's a raised hand from previous question. So in that context, Andreas and Ron, thank you very much for your presentation. And